Let's go on.
Okay. A hanging wire made of iron with a diameter of 0.09 centimeters is initially 2.2 meters long. When a 66 kilogram mass is hung from it, the wire stretches an amount of 1.12 centimeters. A mole of the iron has a mass of 56 grams and its density is 7.87 grams centimeters cubed. Based on the experimental measurements, what is the Young's modulus for the alloy? Well, to be able to find this problem, you have to know what Young's modulus is to begin with. Young's modulus is your stress over your strain, and that can be written as, for your stress equals your force divided by the area, and your strain is your delta L divided by L, your change in L divided by your total length. It can be rewritten as force times length divided by area times delta L. This is your regular Young's modulus. Whenever you go into interatomic with the Young's modulus, you have to keep a few little details in mind. Your area is going to be the cross-section of the wire. So it's virtually a lattice, so therefore it's square. So you have your diameter times your diameter, which gives you your diameter squared. And your change in L is essentially just your stretch in the wire of how much it stretches. To calculate F, you're going to use the spring constant of K times S. After you find that out, you're going to rewrite all the variables that you had here in these terms. You get the KIS of S times D over your area, which is D squared minus S. I cancel out the variables that can be canceled out because all of it's multiplied together. And you get just your spring constant for your interatomic divided by your diameter of the atom. To start the calculations, we're going to find out the diameter of one atom. We're going to do that by taking our density that they gave us. We're going to start with the density. The density that they gave us is in grams centimeters cubed. It is not the SI units for it, and we need all units to be equal and the same throughout the entire problem. So we're going to have to convert it to SI units. And when we convert to SI units, we get the 7.87 times 10 to the third kilograms meters cubed. From there, we're going to calculate how many moles we have to get the atoms. We calculate everything in kilograms, the atoms, and we find that we have 8.46 times 10 to the 28 atoms in the meters for the whole cube. Well, what we're going to do now is just find what one length is instead of the whole cube. So we're going to cube that, and we're left with 4.39 times 10 to the 9 atoms. That is how many atoms they have in 1 meter of the whole spring wire. From there, we're going to divide 1 meter divided by the number of atoms we have to find the diameter of the atom, and we get 2.28 times 10 to the negative 10 meters. Now, we're going to start solving for the spring constant of interatomic. To do that, though, we first have to start off by finding the spring constant for the entire wire. And for that, we're going to use the momentum principle, where, because it's not moving, P is equal to 0. And your F net is your spring constant minus your mass times gravity by delta T. we're going to algebraically go from here to this, where you have your mass times gravity divided by the stretch. Gives you your wire. So from here, we can plug in the variables that they do give us to 66 kilograms, 9.8 meters per kilogram, divided by your stretch. And we also have to convert the stretch into the meters, because it was originally in centimeters. And from there, we get 5.78 times 10 to the 4th newtons per meter. After that, we're going to first calculate the area of the wire. The area of the wire can be looked at the same way as we figure out the area for just one atom. So we're going to take the wire, area of the wire squared, and they give you your diameter for your squareness of 0.9 centimeters. Again, we're going to have to convert it into meters. Once we have it in meters, we have to write it, we have to square it, and we get 8.1 times 10 to the negative 8 meters squared. Now we're going to find the area of an atom. And like was previously said, the area of the atom equals the diameter squared. So we take the diameter, which was the first thing we found, and we get 5.20 times 10 to the negative 20 meters squared. From there, we're going to have to find out the number of chains that they have altogether of atoms. You can find the number of chains by dividing the area of the wire by the area of an atom. You have your two amounts that you just got, and for the number of chains, you get 1.56 times 10 to the 12. Now you need to find your number of bonds on that chain. To find the number of bonds on that chain, you're going to take the length of your wire, which is given in the original problem, by the diameter of the atom that you solved for. So you have 2.2 meters divided by 2.28 times 10 to the negative 10, and that gives you 9.65 times 10 to the 9. Now you can find your spring constant for the interatomic. To do that, you have to use your spring constant of the entire wire, multiply it by the number of bonds you have in the wire, divided by the number of chains. Take all your answers that you got on the previous throughout, and you get 3.54 newton meters. Finally, you can go back, now that you have the KSI, you can go back to your Young's modulus, which is the interatomic spring constant divided by the diameter of one atom. You have your two numbers set, and this 1.75 times 10 to the 12 newtons meters squared equals Young's modulus.